Hello, everyone. Good morning. Thanks for being here. My name's Vinay. I'm a product manager at Snowflake. I'm joined on stage with Shulin, who's on the engineering team. I'll give you a chance to also talk more about your role as you get to your session.
Hi, everyone. My name is Shulin. I'm an engineer, and today I'll be presenting I'll show a demo on many model training in just a bit. Yeah.
Cool. So our talk is focused on this framework called Many Model Framework, and we'll talk a little bit about the use case. We'll apply this to complex time series forecasting, and we'll show you how these are actually very, very pertinent problems as we're seeing across the market. We have a cool demo for you. Would love to also, of course, spend more time taking your questions. So need to start with this safe harbor slide in case there are some things we say that is future looking. Please don't hold us to that commitment. So I want to start with just setting the context for forecasting problems in general. So we, as part of Snowflake, deal with many, many different customers, terabytes, petabytes of data on our platform. And a common pattern we're seeing is how forecasting has become so much more complex today. It's no longer what we saw simple regression earlier. So take the case of a retailer. You want to forecast product sales. You want to make sure that your inventory systems are in the right place. You want to make sure the supply chain is sufficiently optimized to deal with these type of varying demands. And all of this means you have to take in signals from everywhere to make sure you get to this accurate forecasting. So when you're doing things like product level forecasting, you want to make sure you're taking in customer feedback, reviews, sentiments, a lot of multimodal signals. People are uploading videos and images, and everything contributes to the ability to forecast on the success of a product line. Now put that into how this plays out across a time series sequence. You've got non-linear time series. You've got seasonalities. You've got seasonalities within seasonalities. You've got a fall window with long weekends and Halloween weekends, and all of this means there is a very complicated series of windows that you need to make sure that you're capturing in your feature set that reflects the ability to forecast how your sales are going to be. And then think of all the external factors that are contributing to this process. You've got market signals, you've got competitor announcements, you've got geopolitical situations, everything that contributes to your need to make sure that you're forecasting things the right way. Now, this can easily be translated to other scenarios. We've got financial services companies who are doing this on equity forecasting. You want to make sure you're predicting stock forecasts. It's a really, really complex, time-consuming process. And I would say almost a large majority of these use cases are now doing somewhere between an LSTM and a transformer, and the transformers are becoming a lot more common in these types of forecasting. OK, so that is not that new a problem. We've seen this. It's just becoming a lot more common these days. But what is actually becoming a real challenge is trying to do this at these micro-segmented levels. Like, imagine you have a retailer who's got 1,000 product lines, 500 stores, 4 or 5 different geographial locations, and you want to make sure that every one of these micro-segments has this type of detailed forecasting. You, as an implementer, as a technologist, now needs to figure out, OK, I have these complex models I'm training on, probably per SKU times store ID times geography, whatever that key is. That has to then train frequently. I can't just do this once a month, right? You want to make sure your forecast is up to date and it reflects the latest the patterns and indicators. You have to train this weekly, bi-weekly, possibly even daily. And you're training thousands, tens of thousands, hundreds of thousands of these complex models every single time. This means your infrastructure needs to be scaled up sufficiently. Your training needs to be robust and reliant. You need to make sure checkpointing is in the right place. You need to make sure observability is in a good shape. You need to make sure all of this can be automated and deployed in a nice operational manner. This becomes an enormous scaling challenge, which is where we in Snowflake have leaned in heavily to make sure that this is really simple for people trying to implement this type of pattern. So what we've introduced, and we'll show you a demo for really in a short bit, is how we have defined this thing called a many model framework, where effectively what we're saying is you as a user make sure your data set is partitioned. You give us a partitioning key. Your partitioning key could be a combination of your store ID, product ID, and SKU, or whatever that is, right? All you need to do is give us that partitioning key, point us to the set of tables, set of data, wherever they are, and write your training function. Write your PyTorch definitions, write your optimizers, layers, whatever that may be, which you're going to do anyway for a single SKU. Give us these three things, we will do the rest. We will make sure that infrastructure is abstracted away, the orchestration is abstracted away, everything is robust, and you, end of the day, get an end-to-end working pipeline. Not just that we'll train these tens of thousands of models concurrently, we will also make sure they're logged to a registry where you can infer on these logged models with the same partitioning sequence. So I'm sure you can see a lot more in the demo, and wanted to quickly touch on what the simple layering diagram, just to sort of put into place what we're using. A lot of the orchestration and the scheduling is happening through Ray, and we all know Ray is phenomenal at doing a great job at heterogeneous compute, at making sure that the data is pipelined sufficiently for the best utilization of resources. We've seen great GPU saturation coming out of using Ray. So we're happy to talk about how much we've invested in making sure PyTorch on Ray runs really well. At the same time, it's Snowflake data, so you've got large amounts of data that needs to make sure it's streamlined, it's pipelined into these Ray actors, and that's where a lot of the engineering work has gone in. Wanted to touch on a few quick things here. So in addition to what we're calling the many model training or the partition training, which is the third box you see there, there's other distributed frameworks that we've built to make life easier for customers over Ray. So we've got a distributed data connector, which means wherever your data is, your data is in S3, your data is in tables, we will bring it in using Ray into a memory of your notebook or wherever you're running your workloads in a very, very scalable and efficient way. We've got all of the distributed ML training, hyperparameter tuning APIs also built on Ray, and of course, what we're going to be talking to you about today. Cool. So I'll give you a quick intro into this framework, and then I'll hand it right over to Shulin. So what is happening under the hood is we have a Snowflake table where you define so again, the Snowflake table could be any table. This is just a simple database construct. You have a table, you have a partitioning key. What we will do is we will automatically run a query to extract every single partition, in this case you have thousands of these partitions, into its own data frame. Those data frames are then converted into a Ray data set, and that's where the magic of Ray happens. Like each Ray data set is mapped to a Ray actor, and that Ray actor is then fed that data set along with the training sequence we set up in the initial definition. And then all of these are kicked off in parallel. We assign compute clusters as and when they come up. So each time a Ray actor is alive, we connect a node to it. And that way you're given a gradual scaling up and gradual scaling down. So that's also part of the optimization that we've done. And of course, you can use GPU clusters, CPU clusters, combinations of these multi-GPU nodes where you want to train a single PyTorch model on multiple GPUs or multiple nodes. All of these combinations are possible through this framework. Great. So this can be super complicated. We want to keep it really simple, just show you what it looks like in a notebook. And you know, the goal of this demo is the simplicity of the interface and the power beneath it. So I'll hand it over to Shulin to do a quick demo.
Thanks, Vinay. Okay. Let's get it running. All right. Thanks everyone to joining today. Now that we have seen the overall many model training framework architecture, let's dive in and see how it actually works in code. In this demo, we're going to work through a simple synthetic retail data set. We'll train a PyTorch model for each store in parallel to predict the daily sales based on historic data. We'll then scale out the cluster to speed up the training process. And finally, we're going to deploy all the trained models into the model registry and for inference later on. So just to mention, we're not focusing on the modeling part in this demo specifically. It's just going to be basic synthetic data and small modeling. The main real story we're trying to convey here is to showcase the many model training framework that to easily chain, manage, and scale out many of the models that you have in a very efficient way. So as you can see, everything you see here is running inside a container runtime environment. In this case, it's running in a CPU cluster that consists of x64 medium instance that has 6 CPUs on it. But we're going to scale this out later on as part of the chaining process, as you can see. So before that, let's do some basic setup. First, we'll create a Snowflake session object. This is what allows us to connect to the Snowflake data, the raw data that we try to chain with our models on. Then we're going to set up a Snowflake stage, which is used as a persistent storage for saving any many model chaining associated artifacts. That's all the setup we need before we jump into the data parts, right? So the synthetic data, basically, as you can see, it has a multiple of rows. Each row represents a product's daily sales, along with features such as price, promotion, and competition pricing. This data set is relatively small. It covers 150,000 total records, spans through 10 stores, and each store is having 500 unique products in each store. And that's it. So to prepare this raw data for our model consumption, we need a little bit of feature engineering work. So here we are simplifying to creating a sliding 14-day sequence of features. And pairs each sequence with the next day's sales value. So effectively, the model itself learns to focus the next day's sales based on the previous 2 weeks of activity. So the resulting chaining tensor is the number of samples you have, and it's going to be 14 by 3. 14 as the number of past 14 days, and 3 in this case is the 3 features that it's going to fit into the model. Now for the fun part. Let's dive into the actual how do you invoke a many model chaining. So there are a couple of parts related to it. So the first is that we need to define a chaining function. And then next, we need to scale out our cluster accordingly. And then last is that we're going to invoke the API to run that chaining function across all of our chaining workers. And we're going to monitor the process as it's running. So the first step is we basically define this chaining function, the LSTM model, very simple. And then we have a user chaining function. This basically takes in 2 things. It will take in the data connector, which will connect basically the MMT framework under the hood, partition the data, and pass each store partition into this chaining function. So each of these chaining functions will only receive the corresponding store ID partition data. The second argument here is a context object. This context object provides information such as which partition ID is associated with this data that is passing into this chaining function. So here, I purposely throw an error when this chaining function is processing partition 5. And we'll see in a bit how this error is actually surfaced up later on. Moving on, we connect the data to pandas, and we prepare the data into the sliding 14-day windows before we feed it into the model. Then we basically convert that data into a Torch data set and feed it into the data loader. And the rest is just very straightforward Torch chaining. We chain it for a few epochs, and we record the logs along the way. And for now, we basically just print it out, and I'll show you in a bit how those information is actually being captured. So once this is done, before we actually invoke it, we can choose to, with simple one command, we can basically scale out our cluster to have more nodes. So one cool thing about this is the scaling is actually can be done in an asynchronous way. So we don't have to imagine if you have many nodes that you want to spin up, you don't have to wait for all the nodes to be up before you can start running many model chaining. So while the nodes are starting to come up, the many model chaining can start running. And as more nodes come up, they will join the worker pool to take up more chaining work along the way. So let's see. In this many model chaining API, we take in the user function that we defined in the earlier step. We take in the stage name that we created at the first step to persist the artifacts. And we also pass in the run ID here before into the run function. Let's hit a run. Let's give it a run. Just want to point out the run ID is useful for if your notebooks for some reason disconnects, you can use the run ID to cover back the previous result. So you can see there's a Streamlit widget showing you the real-time progress. We separate out the data ingestion and chaining, as what Vinay mentioned earlier. So as soon as one data ingestion is ready to be trained, we will have a worker to pick that up and running it directly. And also we are showing, because we're running in the 2-node setting, as we just scaled out just now, you'll see that there are 2 nodes, the CPU utilization and memory in the real time. But for some more tech-savvy users who would really like to see underlying, like what is the RAID operation you're doing under the hood, we also provide user the direct link to the RAID dashboard. And there, a user can actually have the default native RAID dashboard to investigate any like under the bottom, like the RAID task or actor, resource usage, logs, cluster, etc. Out of box. So all of these are very native in as what RAID provides. So once this chaining finish, here it shows fail, and this is intentional because remember, we previously in our chaining function, we throw an expected failure for a specific partition. So imagine now for a real user, if they run get progress with this specific run that we defined in the previous step, it's gonna show that there's 9 out of 10 partitions. There are 9 partitions that succeeded, but there's one failed one. Let's take a look at, like, say, the first succeeding partition and the corresponding logs associated with that. You will see that it prints out the correct chaining logs as what we defined in the previous step chaining function. And we can also easily get a model weight out from the dead chain model in that partition through the get model call. So this is all the tensor weights as you can see. But what's even more interesting is actually debugging what is actually failing. So there's one failure, and we can easily get that and print out the logs. Note that we retry it for 3 times and eventually fail. So this is the runtime error that we threw in the earlier step. So in the real world scenario, errors does happen. And what we have seen happen a lot is out-of-memory error. So sometimes each partition could have different skews. So when a partition becomes too large or the model complexity becomes too complicated, there's a chance to WOM. And what we have done here is we have built in a WOM detection system that basically we kill the job right before it's about to WOM, and we handle it nicely and surface that error to the user. And as you can see, even if a couple of partitions fail, it's not going to fail the entire many model chaining job. And the benefit of this is if a user is running a very large scale many model chaining workload, they can, say for days or hours, they can literally take a look on the resulting failed partition, diagnose what's going on, and then only rerun the pipeline on those failed partitions instead of the entire partition to save time and cost. So moving on. So after we have chained the 10 models based on each store and product, we're going to log these models to the model registry for inference. So logging to the registry is really straightforward. Here we basically define a partition model. This partition model is basically a model that encapsulates all of the chain models, submodels that we have chained in the previous step. And we get all those submodels in the previous step through the many model chaining framework get model call, and we pass it down to this model context object and to construct this partition model. And after that, we're going to log it to the model registry. And for the time sake, I already did this step earlier. So here we will log a model called partition model and to the registry. Once the log model finish, you'll see in the Snowflake node side UI that there is a model being logged called partition model with a version name called Jolie Squid 2. So you can see the input and output of that model, a typical what this model expects. And what's more is you can click into the artifacts just to see, because in this case we have 10 store ID. So for each store ID, we chain a specific model for it. And you can see the Torch model, and then you can download it to play with it to debug anything on a very partition level if you need it. And we also come with a bunch of other metadata files for users' convenience. So after the model is logged, let's go back to see how we actually run inference on the logged model. So in this case, we are preparing our test data into past 14 days of features. And what this is going to be do is that once we pass this data to our model and call model.run on it, it's going to take in the past 14 days, which consists of many different stores. And our framework is going to be able to route each record to the right submodel that corresponding to that store and run inference on it. So this run will basically run all of these records, and then this is a simple prediction, how a prediction result actually looks like. What this means is basically for store ID 9 and product ID 0, based on the past 14 days of the features that we're passing, we predict the next day's sales is going to be 30 in this case. And that pretty much sums up the demo portion. Let's switch back to the slide. So just a quick note on the performance. So we have done benchmarking comparing this, even running the many model training on a single node. And when you compare it to with the serial manner of running models, we're still showing like as the partition size increases, the MMT started to outperform serial chaining by a lot. And then what's more, if you scale out your cluster from one node to multiple nodes, we see there is a linear correlation between the number of total runtime associated with the number of nodes that you scale up. And this shows that the entire many model training framework is highly scalable across multiple nodes. And we have fault tolerance built into each of our partition chaining section. So each of the user chaining function that we saw earlier, we automatically retry, we handle the womb error out of box, and we provide a nice interface for user to debug if anything goes wrong, and then only retry the fail options, fail partitions if needed. And with that, that should sum up the entire presentation. Thanks to everyone for following along. And now I think we can open up for some questions.
Like all good demos, we can learn best when we get to run these Jupyter notebooks ourselves. Are any of these QR codes, like tutorial or something like that, we need to use?
So the first two are actually generic distributed PyTorch tutorials that you can run on Snowflake. It's trial account compatible, so you can log into Snowflake. Datasets are already there. The first two ones actually point you to general distributed PyTorch. We will publish documentation for this particular framework that we spoke about. It's just getting out of preview as we speak. So the demo that Shulin just showed you, that is not yet on our websites, but you can see something similar in the first two links there.
So on your left here, the failure and restart detection work that you had there was very cool. Thanks for showing that. I'm curious how that works in a multi-node scenario where you might be failing in a collective where the other node is waiting on the node that actually failed. Do you kill the whole job and restart it, or what do you do in those scenarios?
Are you talking about a scenario where each chaining function is running across multiple nodes or in a single node setting?
Correct.
Oh, yeah, so good question. I think the question is about like in a many model training framework, if you run each of your training function across multiple nodes, and if one of the nodes fail, will it affect other workloads, right? So in this case, I think we do. Technically, we have actually we enforce some sort of resource boundary. Each node is only allowed to use up to a certain amount of resource. Once it gets across to that level, we kill that job automatically. So we will kill that specific partition job, and it will mark that job as failing, and then we'll throw an error in that log saying that this job failed because it worms out after it surpassed this extra memory space. And it's up for the user to actually retry with a larger node, or basically scale up to more nodes, basically. Yeah.
Yeah, I think another way of answering that is auto scaling is not yet in place, so that's something that we want to work on.
A question I had was like, sometimes happens because my CPU and GPU, like if my data processing is happening on some CPU kind of thing, and then I'm loading the model training on GPU, is there a way to apply a little bit of back pressure? Or is it like you have to materialize the data frame in memory and then train on that, so it's kind of separate, disjointed?
Yeah, that's a very good question. So I think in the you're right. In the existing pipeline we already show, we doing the pipeline between the loading data from Snowflake, and then loading data from that into GPU, from CPU to GPU also incurs additional time. Right now, we haven't done specific optimization on that yet, but it's definitely something on our roadmap. This will be more related to how user actually define their chaining function, and if there's any optimization, they can do it. But we're also thinking about, from a framework's perspective, what we can do about it as well. Yeah, but that's a good question.